fellow viewers, welcome back to class. I'm super excited to welcome you guys back to Master Builders Online Academy. You are welcome, you are welcome, you are welcome, you are welcome, you are welcome once again. Now, if you are new in this channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting videos. This is very important because even while you are asleep or you are doing other domestic work, you will be notified anytime we upload mind-blowing content. Lest I forget, do not skip any part of this video. This is for your own advantage, and ensure that anytime you are set to watch and to learn new concepts from this platform, do not welcome any form of distraction. This is for your own good. Now, if after watching this video from beginning to the end, you do not understand it, guys, watch it over and over and over again. You will understand the principles. And if after replaying the video over and over again, you have questions to ask, guys, do not hesitate. The comment section is there to accommodate your questions. So therefore, slide to the comment section and make your questions known to us. We will answer your questions to your satisfaction. And if this is understood, therefore, don't forget to like this video, share this video, and make your necessary comments. Now, guys, let's get to the business of the day. On the board, we are still looking at the design of reinforced concrete beam. And now we have the second problem on the board. All design problems under beams, all beam design problems are the same. The same principle, the same steps are applicable. All you need to know is to know whether you are designing as singly or you are designing as doubly. Now, let's look at the question. Now, we are asked to determine the area of reinforcement required in the section shown below if the design moment is equal to 290 kilonewton meter and the characteristic material strength are F of C is 30 and F of Y is 460, and this is the diagram that we're given as shown below. So this is the cross section of the beam. Now, looking at the cross section with these symbols that we have here, it is an indication that this reinforced concrete section is to be designed as doubly reinforced. Why? Here I already have AS prime at the top. Now I have AX. With this sketch, the examiner is already telling us that we should design for both top and bottom. But before we will do that, we will have to test run and see if this section is actually going to be designed as doubly. The presence of this AS prime does not necessarily dictate that this structure should be designed as doubly, except that the values that you have here correspond. So the values you have here can disagree with the notations you have here. So let's test run on our own and check if truly this section is to be designed as doubly as the examiner or the author has stated. So if our parameters here, after taking one or two steps, we find out that this section is to be designed as doubly, then we'll do that. But from the question, we were only asked to provide the reinforcement. But from the sketch, the reinforcement requires both tension and compression rebars. Are you there? So now let's start. First is to extract the given parameters as usual. So we have given. Now we were given a moment capacity, the design moment to be 290 kilonewton meters. And we said that anytime we are given moment in kilonewton meter, we solve with newton millimeters. And to have this done, you must multiply. Then you must replace 1 kilonewton meter by 1 million newton millimeters. And this, we have this to be what? 290 multiplied by 10 raised to power 3 newton millimeters. Having obtained this, the next is that from this diagram, we have that D is equal to 260, as you can see, and that D is equal to 40, as you also can see from this sketch. Then we have D prime, like I explained before, that from the top section of the compression zone to the center of the top reinforcement, that is what you have as the what effective depth of the tension reinforcement. So from this top now to the center of the bar, that's what we are given. That means this is D prime. Therefore, D prime is already given as 50 millimeters. Then another thing that is given here is the strength of steel and that of concrete. So F of Cu is equal to 30 Newton millimeter squared, and F of Y is equal to 460 Newton per millimeter squared. Now from the question also, we are asked to find AX and AX bar. These are the two things we are asked to find. But like I said earlier, from what we have here, it is not enough for us to believe or to have the mindset that we are going to design this session as both singly and doubly. That the parameters that we have here can prove otherwise. And let's check if actually we are going to design this beam as doubly reinforced or as singly reinforced. Now, the first thing you always do is to start your design from what design load. And I said earlier that you only design load, you calculate for design load when you are given the loadings, which is the live load and the dead load. From the question we have here, there is no load. So that means there is no need for designing load. Now, after calculating for your design load, the next thing is to design your moment. Now, there is no need for us to design moment because we were already given the moment. Now that we have moment, the step after calculating for moment should be the next. And that step is calculating for what K, which will tell us whether we are designing this session as doubly or as singly. Hope you are following with this class. This is very, very important. And that's why you need to avoid every distraction. Because there are criteria. You don't just solve. This is not mathematics or physics or chemistry that you just solve direct. This is design, reality. Are you there? So you need to understand that conditions, boundary conditions matters here. Okay, now, so let's test run whether this structure is to be designed as singly or as doubly. First, we have the ratio of the moment. F of Cu BD squared. Now, moment here is 290 multiplied by 10 raised to the power 6. All over. This guy is 30 multiplied by 260 multiplied by 440 all squared. And K would have given us 0.192. This is the value we have when we divide this numerator by this denominator. This is the outcome. Now, from what we can see here, we find out that the value of K is greater than 0.156. And anytime the value of K is greater than 0.156, the section is no longer safe to be designed as singly reinforced. Rather, it is now safe to be designed as doubly. So truly, from this indication that we have here, we are to design this structure as doubly reinforced. So that we have, since K is equal to 0.192 and is greater than what? 0.156, then design as doubly reinforced. Now that we are to design this as doubly reinforced, listen carefully. The next thing you are quickly going to do is B. Now, once you find out that the value of K is greater than 0.156, there is no need to calculate for lever arm factor, LA. There is no need. Why? Because if you calculate for the lever arm factor, you are going to have a value less than the lower limit, which is 0.775. Anytime the value of K is more than this, whatever you calculate with that value must be less than this. So what you do is that anytime the value of the lever arm factor is less than the lower limit, you make use of the lower limit. So for doubly reinforced, all you just need to do is to take LA as this. But for those who are Thomas, who wants to see first before they believe, then I will take this step, okay? But for the purpose of exam, you don't need to do all of this. Once you identify that a beam is said to be designed as doubly, there is no need to calculate for the lever arm factor because it will be useless. But let me solve the useless aspect of it for the sake of the Thomas Didymus. Now, we have that LA is equal to 0.5 plus the square root of 0.25 minus k over 0.9. Now, if we impute the value of k, we have this as 0.5 plus the square root of 0.25 minus k is 0.192 over 0.9. Everything is inside square root. And when we calculate, we have 0.691. This is what we have. Now, the liver arm factor calculated is this. But when we look at this value now, it is less than the lower limit. So therefore, anytime the calculated liver arm factor is less than the lower limit, you make use of the lower limit. And understand that for every doubly reinforced section or concrete beam, liver arm factor will always be less than the lower limit. If this is taken, then I deserve a hand of applause. Now let's continue. So therefore, since the liver arm factor calculated is less than the lower limit of the liver arm factor class, hence we will make use of the liver arm factor. This is a boundary condition. So therefore, adult LA is equal to 0.775. Then what will be my liver arm factor? Z D multiplied by liver arm factor, and this will give us 0.775 multiplied by 440. And when we multiply this would have given us 341 approximately. 341 millimeters. This is the liver arm factor. Now, secondly, now that you calculate for the liver arm factor, the next thing you will calculate for is the ultimate moment of resistance. And I explained earlier that there are two ways to know whether you are to design a beam, either as a singly or as doubly. One is to check with the value of K. Now we have ascertained that the value of K is greater than this, and such we are designing as doubly. But let's check with the other method. What was the other method? We said that the ultimate moment of resistance to be offered by the concrete must be less than the applied moment. Now, the applied moment here is 290. That means for this system to be designed as doubly now, it shows that the ultimate moment of resistance of this concrete itself is less than this value. Let's validate as we calculate for the moment. It must be calculated for once you are designing a doubly reinforced concrete beam. Okay, so we have ultimate moment of resistance in concrete is equal to 0.156 F of Cu BD squared. So Mu would have given us 0.156 multiplied by 30 multiplied by 260 multiplied by 440 all squared. And 236 multiplied by 10 raised to the power 6 Newton millimeter. So to convert this to kilonewton meter, you have 260, remove 10 raised to the power 6 by 1 kilonewton meter. So this is what we have. So this is the capacity of the concrete. Now we know that this is the capacity of the concrete, but we want a load greater than this to act on it. In fact, that is the load acting on it. And we cannot do anything. The only thing we can do is to what? Ensure that we put the section in a state where it can carry this load. We cannot reduce from this load. So since we cannot reduce from this load, what do? We need to increase the strength of the concrete. That's the reason why we now provide for top reinforcement, so that we'll be able to what? Carry the load. Is this clear? Now, okay, if this is taken, then the next is to calculate area of what bar is M minus Mu all over 0.95 Fy open bracket D minus D prime. This is area millimeter squared. This is the SI unit. Okay? This is how you calculate. So, what you use to actually obtain the top reinforcement is the extra moment between the ultimate moment of resistance of the concrete and the applied moment. The difference between them is what you use to provide reinforcement for the top. Okay? To attain equilibrium or stability. Now, if this is understood, what is the moment due induced on the structure or the applied moment? The applied moment is 290. So we have 290 multiplied by 236 or multiplied by 10 raised to the power of 6 all over 0.95 multiplied by 460 multiplied by effective depth is 440 minus effective depth of the compression bar is 50. So guys, when you simplify, multiply out, the resulting value for this is 317 millimeters squared. This is the area of the top bar, which is the what? The compression bars. Now that is what you have. We have successfully obtained the value of this. Now this is the required area. Then you need to provide area by using the same table. So when you go to the table, just look out for what? Area that is greater than this. And you will pick the area. Now, the next thing we do is to quickly calculate for the area of the tension bars. And for us to do that, we will quickly state the formula and proceed. Well, the area of the tension bar, AS, is equal to MU all over 0.95 Fy of Z plus AX bar. It's as simple as this. All I need to do now is to substitute. So at this point, this will have given us 236 multiplied by 10 raised to the power 6 all over 0.95 multiplied by 460 multiplied by the lever arm is 341 multiplied by 341. Then plus area of compression bar, the required area. And the required area is 317. Now when we simplify everything here, we will have 1584 plus the area required at the compression zone, which is 317. And when we get this done, we will have this as 1901 millimeter squared. This is the area required at the tension zone. So now all we need to do now is to go to the table and provide area of reinforcement. That's all. So for the bottom, for the bottom bar, which is the tension bar, we just go to the table and say provide. Now go to the table as usual. Just go to the table as usual. Trace area number of reinforced bar or group of bar of this, if you see it that way. Okay, it is either you have it as area of bars or group reinforcement of group of bars. Okay, so from here now we have group of bars where you have numbers and you have the bar size as the column, then the number of the bars as the row. Now I will just come here and look out for where I can get an area greater than 1901. So that means I need to start looking for what? 1902, 903 till 2000. Are you there? Yeah. So now, how do we get this done? Just go to the table and look for where you can see 19 and above. Now, if I come to number 4, I want to use number 4. I will have 1964, 1960, 1960. So if you trace this now, check for number 4, trace it and you see 1960. When you trace it down to the bar size, you will discover that the bar size corresponding to that value is 25. All right. So when we trace it, we find out that is what 25. Then we will provide 4y25 millimeter bar. Are you there? This is what we have, and the area corresponding to that is equal to 1960 millimeters squared. Now this is for what? Top. Then for the bottom, we can also provide. Now, since this is 4, y25, I can also look for another 4, but of a lower diameter, because this is the value we are supposed to provide for. And we have 317. So we are expected to look out for 317. We have a value greater than 317. So assuming I want to provide 4, 317 would have been other 4y12. So another person can provide 4y12. Now from here now 317, I have 452. 452. I'm using number 4. As you trace down, you have 452, and the bar size corresponding to that is 12 mm. So you can use 12. Then 4y12. Then another person can say, okay, I will not use 4y12, let me use 2. Then when you come and trace for 2, you will have 2y16 for 402. So you can say, okay, provide 2y16 millimeters bar, and the area corresponding to this is 402 millimeters squared. But if another guy now says, okay, no, me, I want to provide 4y12. Like I said, the higher the number here, the lower the bar size. So when I have 2 here, 2 numbers, 2 steel, it has a diameter of 16. But if I have to increase the number, therefore I will decrease the diameter, which we have from the table here. So if another person provided this, would have given us 452 millimeter. You are all right at the same range. You are still very correct. So you can provide 4y12 as your tension reinforcement. So in this lesson, we have successfully answered the question where we were asked to provide the reinforcement required for a beam section that is to resist a bending moment of 290 kilonewton-meter with the following characteristic material strength: F of Cu 30 Newton per millimeters and square, and F of Y equal to 460 Newton per millimeter square, to an effective depth of 410 and the width to 260. This is all about this question. We are done with this question. So guys, like I said earlier, all beam sections are designed the same way. Yours is to identify whether you are designing it as a singly, then you follow singly design procedures, or as doubly, which will equally follow the doubly design procedures. It's as simple as this. So principles, when you know principles, you become a principal. And equally, when you understand boundary conditions, you will not overstep your boundaries. This is very, very important. So if you find this content helpful, guys, consider subscribing to this YouTube channel, share this video, like this video, and make your necessary comments. I know you won't like to miss the next class, so you can quickly check the description below where you will find the link to the next lesson. Love you guys. Thank you for watching. See you in the next class.